In this video, we're going to look at two new words, superposition and interference. And I'd like to begin with a story. I once made a mistake no physicist should make. I'd wandered out to a small island carrying my son, had a picnic, and then decided to wade back. In the meantime, the tide had started to come in, and rather gentle waves were diffracting around the sides of the island to cross over in the region between the island and the shore. The mean depth of water was no more than a metre, so I started to wade back across the 50 metres or so that separated us from the beach. The waves from each side caused a swell of no more than 25 centimetres, but where they crossed, the water rose 50 centimetres, and I had to hold my son above my head to keep him safe. I had forgotten the principle of superposition. And what we're going to look at here is what happens when waves meet, when we've got more than one source of wave and the waves meet. And so the story talked about these kind of wave fronts heading towards an island. The island is like a barrier, and we know that if the wavelength and the size of the barrier are kind of the same or similar, we get this diffraction, and it's that meeting point of the two sets of waves that was important. Now, the good news is, I think this is all fairly intuitive. So you've got two waves shown, A and B, and I want you to think now, what do you imagine it looks like when they meet and then carry on? In other words, if we had to draw the resultant wave, what would it look like when they meet and what would it look like when they carry on? Give you a few seconds. Okay, if you drew or thought something like this for when they meet, well done. Okay, that is the resultant of the two waves. We are adding the displacements together at all points and we're working out a resultant wave. What about when they carry on? If you got this, then well done. The waves carry on almost unaffected by the fact that they've met. They carry on as they originally were. That is the principle of superposition. Okay, now I've used the language of adding displacements with you. So let's see if you can think about how then that relates to this diagram here. Again, I'll give you some thinking time. What does it look like for the resultant wave when those waves meet and then carry on? Okay, if this is what you thought happened as the waves meet, well done. They appear to cancel out. And then if this is what you thought when they carry on, again, well done. It's as if they've never met. They carry on as if that meeting had never happened. So this is the interesting part then of what we're looking at, because for a moment in time, those two waves completely cancelled out and they seemingly have disappeared only to reappear again and carry on. And the important point here is that you are adding displacement, and displacement is a vector quantity. Okay, so if the starting point was this, that's the maximum displacement of wave A, that's the maximum displacement of wave B. When we add them together, we're adding a positive and a negative quantity together, and they add up to zero. Okay, we see this in real life. Sometimes in the ocean, when you're right out in the middle of the ocean and there's quite a lot of waves around you, you have these moments in time where the water goes still and then the waves reappear. It depends on how those waves have met. And what we've just done here is applied what we're going to call the principle of superposition. So in front of you now, you've got a kind of step-by-step meeting of waves. And what is being shown to you is the resultant wave. And the way that that resultant wave has been generated is we are adding the displacements at each point from the two individual waves and showing the result of that. So in words then, what is this principle of superposition all about? When two or more waves meet, we say they superpose and then continue. The resultant displacement at any point is the sum of the displacements of the individual waves. Okay, the idea that we're adding displacements at each point along the wave, working out the resultant, and remembering that displacement is a vector. So when you add up vectors, you can add up with something that is bigger or smaller than what you started with. And we're going to give a name to this overall effect. We're going to call this interference. So back to the story again, we had two sources of wave diffracting around the island. They superposed. To work out the resultant wave or the resultant displacement, we would add the individual displacements of each of the two waves. And what we would observe with our eyes is a much deeper wave, and we would call that interference. Now we look at two particular types of interference, almost like the two extreme types of interference. The first we're going to call constructive interference, and that occurs when waves arrive in phase. Now what does that mean? In phase means that the peaks and the troughs are perfectly aligned. Okay, so peak meets peak, trough meets trough, peak meets peak, trough meets trough. So we would say that those two waves are in phase, so therefore they interfere constructively. And so the resultant is equal to the sum of the individual displacements. So let's imagine that this wave here has a maximum displacement of 2 meters, and this wave here has a maximum displacement of 1 meter. Then the resultant would be a wave with a maximum displacement of 3 meters. Okay, the overall displacement is greater than the individual displacements of the individual waves. Conversely, the opposite of constructive interference is what we're going to call destructive interference. Okay, and that occurs when the peak of one wave coincides with the trough of another wave. Okay, so now we've got peak meeting trough, trough meeting peak, peak meeting trough. And so now when we add up the displacement, so if I add that maximum displacement to that maximum displacement, if this wave has a maximum displacement of 2 meters, that would be minus 2 meters. And when I add those up, I get to 0. And when I repeat that at all points, they always add up to 0. Okay, so we're going to call that destructive interference, and we're going to say that those two waves aren't out of phase. We're going to say they are in antiphase, and the word anti means opposite. Okay, so the phases are kind of opposite, so the peak of one wave meets the trough of the other wave. Okay, so we've got the principle of superposition. We've got the idea that it's displacement that we're adding. We get a resultant wave, and what we observe is interference. And there are two types of interference, either constructive or destructive.